how to explain the Fermi-Dirac distribution function, etc. I will see today. So Fermi-Dirac distribution function represents the probability of electron occupying a given energy level at absolute temperature, okay, absolute zero temperature or at any temperature T. The expression for Fermi-Dirac distribution is given by f of E is equal to 1 divided by 1 plus e to the power E minus EF divided by kBT, where EF is called as Fermi energy, E is the energy of the electron, Kb is Boltzmann constant, and T is the absolute temperature. Okay, so basically this f of E is called as a distribution function or Fermi-Dirac distribution function, which explains the probability of occupation of the electron in the energy level of energy E. A energy level alli electron occupy ಆಗ್ತದೋ ಇಲ್ಲೋ ಅನ್ನೋದನ್ನ this Fermi-Dirac distribution function explains. So FD statistics deals with particles with half integral spin. Basically, Fermi-Dirac distribution function applies to particles with half integral spin, such as electrons, protons, neutrons. They are all having half integral spin. So here it applies. The particles which obey Fermi-Dirac distribution function are known as fermions. They are called as fermions. Okay, the particles which obey the Fermi-Dirac distribution function are called as fermions. Okay, the examples are electrons, protons, neutrons, etc. Okay, so this is the expression which explains the probability of occupation of the electron. You remember this particular point. F of E is a Fermi-Dirac distribution function which explains the probability of occupation of electron in the energy level of energy E. Next, what do you mean by Fermi level and what do you mean by Fermi energy? So for a metal containing n atoms, there will be number of energy levels in each band. Okay, so there will be formation of bands because of the atom and ion interaction. Okay, so a metal containing number of atoms, there will be number of energy levels or energy bands. So based on that, the band theory of solids is developed. So conduction band, valence band are defined in accordance with band theory of solids. According to Pauli's exclusion principle, each energy level can accommodate a maximum of 2 electrons, one electron with spin up and another with spin down. Okay, so only 2 electrons can be occupied in a given energy level. There are large number of energy levels, but Pauli's exclusion principle says that no 2 electrons can have same set of quantum numbers. So definitely the given energy state has certain quantum numbers. With that, one electron with spin up and one electron with spin down can have different spin quantum number. Okay, because of that, 2 electrons can be occupied in a given energy state. That is in accordance with Pauli's exclusion principle. At absolute zero temperature, 2 electrons with opposite spins will occupy the lowest available energy state. Consider the case at absolute zero temperature. Then in the lowest energy state, 2 electrons can be occupied, because you know that in every energy level, 2 electrons can be accommodated there. The next 2 electrons with opposite spins will occupy the next energy level and so on. So next 2 electrons will occupy the second level, next 2 electrons will occupy the third level, next 2 fourth level, like that. So each energy level can accommodate only 2 electrons in it. Okay, and those 2 electrons should have opposite spins. That is also very important point. Okay, so that each energy level can accommodate 2 electrons. Suppose there are certain 10 electrons. So 5 energy levels can be occupied. The 6th energy level should be empty. Okay, at absolute zero, all the lower energy levels will be occupied. At absolute zero, all the lower energy levels are occupied. In this case, you can find the topmost energy level which is occupied by the electron at absolute zero temperature. You can find out, and that energy level is called as Fermi energy level. Okay, so you accommodate all the electrons from the lowest level, first level, second level, third level, like that. So depending on the number of electrons, the number of energy levels will get filled, and above that energy level there are no electrons, so all the lower energy levels will be filled with the condition of Pauli's exclusion principle. Only 2 electrons can be accommodated in each energy level. In this case, the topmost energy level occupied by the electron at absolute zero temperature is called as Fermi energy level. That is called as Fermi level. The energy of highest occupied level by the electron is called as Fermi energy. Energy of that level is called as Fermi energy. So that is how we can define the Fermi level and Fermi energy. So Fermi level is the topmost energy level occupied by the electron at the absolute zero temperature. Okay. The corresponding energy of that energy level is called as Fermi energy. So this Fermi energy will be different for different metals. Okay, ಬೇರೆ ಮೆಟಲ್ಗೆ ಬೇರೆ Fermi energy ಇರ್ತದೆ. So based on the number of electrons and based on the electron configuration, based on the nature of conduction and valence band, this Fermi energy will vary from element to element. Okay, but you remember Fermi energy is the topmost energy level that is occupied by the electron at absolute zero. So at absolute zero temperature, you have to observe that. Okay. So this diagram shows the clear picture of Fermi energy. Let us take, there are number of electrons and there are number of energy levels. Okay, number of energy levels are there. So each energy level can carry 2 electrons in it. At absolute zero temperature, when T equal to 0 Kelvin, the lowest energy levels will get occupied. And this is the topmost energy level which is occupied by the electron. Above that, there are no electrons. Okay. Above that Fermi level, there are no electrons. Okay. And here, this is the Fermi level. Okay. This is the Fermi level. And the energy of this energy level is called as Fermi energy. Okay. And we do denote the Fermi energy by the term EF. Okay. We use the term EF to represent the Fermi energy. Okay. So basically, the energy levels below the Fermi level are fully occupied. They are completely filled. The energy levels above the Fermi level are always empty. Okay. Fermi level ginta ಮೇಲಿರೋ energy levels empty ಆಗಿರುತ್ತದೆ. Fermi level ginta ಕೆಳಗಿರೋ levels ಏನಾಗಿರುತ್ತದೆ, they are completely filled. That's why this Fermi level basically separates fully occupied level and unoccupied levels. Okay, so it acts like a boundary between fully occupied levels below it and unoccupied levels above it. So therefore, the energy of the highest occupied level at 0 degree absolute is called as Fermi energy, and the energy level is called as Fermi level. Already I have explained that. The Fermi energy is denoted by EF. All the energy levels below Fermi level are completely filled. Okay, below Fermi level, the energy levels are completely filled, above which all energy levels are completely empty. Okay, Fermi level kinta mele, the Fermi energy levels are completely empty, and that is true at absolute zero. Okay, so next we will see at temperature above absolute zero. Suppose the temperature is increased above absolute zero, the electrons get thermally excited and move up to higher energy level. So what will happen? They will go to the higher energy levels, so that Fermi energy will change or Fermi level will change. Okay, you can find some of the energy level which are occupied at certain finite temperature other than 0 degree. Okay, as a result, there will be many vacant energy levels below as well as above the Fermi energy level. So what happens? The highest occupied level will be more having the more energy compared to the Fermi energy. ಅವಾಗ ಏನಾಗ್ತದೆ, ಆ highest occupied level ಗಿಂತ ಕೆಳಗೆ ಕೂಡ ಕೆಲವೊಂದು energy levels ಏನಾಗ್ತದೆ, vacant ಇರಬಹುದು. That is true at T not equal to 0 Kelvin. So under the thermal equilibrium, the distribution of electrons among the various energy levels is given by the statistical function f of E. So this applies even at a t equal to 0 Kelvin and t not equal to 0 Kelvin. So it specifically gives the distribution of electrons in the material, okay, having certain number of energy levels. The function f of E is called as Fermi Dirac distribution function. So this explains the distribution of electrons, and this gives the probability of occupation of given energy level under thermal equilibrium. So whether that energy level is filled or not, that can be identified by analyzing this f of E. Okay, that can be done by analyzing this Fermi Dirac distribution function. Let us see. Let us consider different cases at absolute zero, how it varies, etc. So let us consider different cases by considering the Fermi Dirac distribution function. Okay. So Fermi Dirac distribution function is given by f of E is equal to 1 divided by 1 plus e to the power EF, E minus EF divided by kBT, where EF is the Fermi energy, that is the highest level occupied, highest energy level occupied by the electron, okay, at absolute zero, that is EF. E is the energy of the energy level whose probability of occupation has to be found, okay, that is energy of electron. Kb is Boltzmann constant and T is the absolute temperature. Let us take different cases. Case 1, if f of E for E less than EF, suppose energy of the electron is less than EF, okay, at absolute zero. So definitely we know that the energy levels having lesser energy of the Fermi level, less than EF, are completely filled at absolute zero. Okay. So when E is less than EF and T equal to 0 Kelvin, you substitute here. E is less than EF, therefore E minus EF is negative and T is 0. So it is 1 by 0 is infinity with negative sign. So this will be e to the power minus infinity. So f of E will be equal to 1 divided by 1 plus e to the power minus infinity you will get. So e to the power minus infinity is 1 by e to the power infinity. So this is basically 0. So that's why f of E is equal to 1. So probability of occupation of the energy levels less than EF, so that is energy level below the Fermi level, are completely filled. That is probability is 1. Probability is 1 means 100% occupation of the electrons. So there is a probability, 100% probability of occupation of electrons in the energy level less than EF. Okay, so that is f of E equal to 1 for E is less than EF and at absolute zero. This implies that at absolute zero temperature, all the energy levels below EF are 100% occupied, which is true from the definition of Fermi energy. So according to definition of Fermi energy, it is observed to be true. Okay, definitely all the energy levels less than EF are 100% occupied. Okay, next you will see. Second case, if energy level above the Fermi level is observed, what is observed for energy level above the Fermi energy? So f of E for E greater than EF at T equal to 0 Kelvin. Okay. When E greater than EF and T equal to 0 Kelvin, just substitute for E and T, you will get 1 divided by 1 plus e to the power infinity. So if you substitute E greater than EF, this will be positive. If T is 0, this becomes plus infinity. So it will be 1 divided by 1 plus e to the power infinity. So e to the power infinity is infinity, therefore that's why 1 by infinity you will get, that is equal to 0. Okay, so probability of occupation is 0. Okay, for energy level greater than EF at absolute zero. This implies that at absolute zero temperature, all the energy levels above Fermi energy are unoccupied. So probability is 0 means you cannot find the electron in that energy level. which is true from the definition of Fermi energy. According to the definition, we know that all the energy levels above the Fermi level are empty. They are unoccupied. The energy levels below the Fermi level are completely occupied. So probability is 1 if energy is less than EF. Probability is 0 if energy is greater than EF. Okay, just to remember that. Case 3 will take. What happens if energy is equal to EF? Okay, what is the probability of occupation of the energy level which is equal to Fermi energy? Okay, at a T greater than 0. So let us take the case where T is greater than 0. T is temperature is finite. Okay, so when E equal to EF, what will happen? Just to substitute here, when E equal to EF, this becomes 0. T is finite, so this becomes e to the power 0. Okay, so here the exponential to the power 0 you will get. So e to the power 0 is 1, you will get 1 divided by 1 plus 1. The answer is 1 by 2. Okay, therefore probability of occupation of Fermi energy is 50%, or it is half for E equal to EF at T greater than 0 Kelvin. Okay, so therefore at certain finite temperature, the probability of occupation of Fermi level is half. Probability is half. Okay, if E is less than EF, the probability starts decreasing from 1 and reaches 0.5. At E equal to EF and for E greater than EF, it further decreases. In conclusion, the Fermi energy is the most probable or average energy of the electrons in solid. So probability of occupation is half, means at least one electron will be found in Fermi level. Okay, so 2 electrons can be occupied in a given level. So at least 1 electron can be found in Fermi level. Okay, if energy is greater than Fermi energy, or okay, less than Fermi energy, then probability starts decreasing. Okay, from 1 and it reaches to half. And probability of Fermi level occupation is half. That is very, very important concept. Okay, so therefore Fermi energy gives you most probable energy or average energy of the electron in the solid. Okay, so that is the importance of Fermi energy. It is the highest occupied energy level at absolute 0, but at finite temperature, the probability of occupation of Fermi energy level is half. That is very important concept. So let us study this particular Fermi energy. I will try to draw the graph here. Energy levels with energy less than Fermi energy are completely occupied because probability of occupation is maximum, or it is equal to 1. Whereas the energy levels with energy greater than Fermi energy are unoccupied. Above the Fermi level, the energy levels are unoccupied because the probability of occupation is 0. That is minimum for them. That's why, therefore, Fermi energy level separates the occupied and unoccupied energy levels at absolute 0. Also, Fermi energy or Fermi level is the highest occupied energy level at absolute 0. If you plot the graph, the Fermi Dirac distribution function versus energy, the energy of energy level less than EF are completely occupied, whose probability is 1. Above EF, probability is 0. So there is a sudden drop at EF. The energy levels below EF are completely occupied. The energy levels above EF are unoccupied. This is true at T equal to 0 Kelvin. So F of E is equal to 1 for energy levels less than Fermi energy, and F of E equal to 0 for the energy levels greater than Fermi energy. So this you can remember at absolute 0. So how to represent this Fermi Dirac distribution function at finite temperature? This is at a T equal to 0. At finite temperature, what will happen? This is the graph. Okay, this is how the graph varies. And at absolute 0, a step function you can observe, a sudden fall step function. But as the temperature increases, so there is a slight modification in the Fermi Dirac distribution function. Some of the energy level can get occupied because of the thermal excitation. Okay, as the temperature increases, some electrons can move above the Fermi level, but the probability of occupation of energy EF is always equal to half. So at any temperature, so the curve will cut this half of probability. Okay, so as the temperature increases, the probability of occupation of energy level F of E starts to decrease from 1. So it starts to decrease as the temperature increases. So up to this point, all the energy levels are filled. Then some of the energy level may be empty, and you can find some of the energy level that may be filled above the EF also at T greater than 0 Kelvin. When E equal to EF, when temperature is greater than 0 Kelvin, the probability of occupation of Fermi energy level is half, just as I have proved. Therefore, Fermi level is the energy level for which the probability of occupation is 50% at a temperature greater than absolute zero. So if you want to define the Fermi level at greater than absolute zero, when finite temperature is considered, then the Fermi level is the energy level whose probability of occupation is 50% at the temperature greater than absolute zero. That is also another definition for Fermi level or Fermi energy. So for any temperature T greater than 0 Kelvin, the Fermi level will have the same probability of occupation, which is equal to half. If you take any temperature, whatever may be the temperature, so the term in the denominator will be always e to the power 0. Okay, if you put E equal to EF, E minus EF becomes 0. Whatever may be the temperature, this term, exponential term, becomes e to the power 0. So that's why this becomes 1, and probability of occupation is always equal to half if you take any temperature greater than 0 Kelvin. So that's why the curve will cut this particular point, and any temperature, if you consider any temperature, the curve will cut this particular point. So it will have the 50% probability corresponding to Fermi level. So at absolute zero, the step function is observed. So all the energy levels below EF are completely filled. That is how we can understand the Fermi Dirac distribution function and Fermi energy at 0 Kelvin and temperature greater than 0 Kelvin. Okay. So next we will consider another small concept called Fermi sphere. So you know that Fermi level is the highest energy level occupied by the electrons at absolute zero. That is according to definition. If the energy states are represented in momentum space, suppose you represent the energy state in momentum space, the energy levels specify the concentric circles with origin as their center. Okay. So you know that phase space is having different coordinates. It may be represented by means of momentum coordinate, energy coordinate, etc. Suppose you represent these energy state in terms of momentum coordinate. You can represent the energy as p square by 2m. Kinetic energy E is equal to p square by 2m. So if you convert the energy state into momentum space, you will get p square by 2m. Otherwise, p square is equal to 2me. So that is equation of a circle. Okay. So p square is equal to 2me is an equation of a circle where 2me is representing the radius of the circle. Okay. And that is how you can represent the energy state in the form of spheres or concentric circles in a momentum space. The energy levels occupied by the electrons lie within the sphere of radius pf, where pf is called as Fermi momentum. Okay, if you consider a sphere of radius pf, all the electrons will be occupied inside that sphere, above which a sphere na horagade electrons occupy agodilla antali. This is only representation. Okay, graphical representation of energy states in momentum space, that you remember properly. The sphere with radius equal to Fermi momentum is called as Fermi sphere. Okay, that sphere is called as Fermi sphere whose radius is Fermi momentum. PF. So basically PF, that is Fermi momentum PF, is represented as square root of 2m EF. Okay, where EF is the Fermi energy, you can represent Fermi momentum PF as square root of 2m EF. I will come to that later. The surface of the Fermi sphere in momentum space is called as Fermi surface. Okay, so the surface of that sphere is called as Fermi surface. I will try to show it graphically. All occupied energy levels lie inside the Fermi sphere. The Fermi level lies on the surface of the Fermi sphere, above which the energy levels are unoccupied. Fermi surface represents the Fermi level in momentum space. ಇಲ್ಲಿ ನಾವು ಏನು ಮಾಡಬೇಕಂದ್ರೆ ಎನರ್ಜಿ ಸ್ಟೇಟ್ಸ್ ಅನ್ನು ಒಂದು ಸ್ಪಿಯರ್ ಅಂತ ಕನ್ಸಿಡರ್ ಮಾಡಬೇಕು. ಇಫ್ ಯು ರಿಪ್ರೆಸೆಂಟ್ ಎನರ್ಜಿ ಸ್ಟೇಟ್ ಇನ್ ಮೊಮೆಂಟಮ್ ಸ್ಪೇಸ್, ಸೊ ದಟ್ ವಿಲ್ represent a sphere, and that sphere will have radius equal to Fermi momentum, that is represented as PF. Okay, so all the states are lying inside the Fermi sphere because above the Fermi level there are no energy states occupied. All the occupied energy levels are inside the Fermi sphere. The surface of the Fermi sphere is called as Fermi surface, and basically that Fermi surface is a boundary which separates the occupied level and unoccupied level. All the occupied levels are inside the sphere, all unoccupied levels are outside the sphere. That's why Fermi surface basically separates the occupied levels and unoccupied levels in the momentum space. Okay, so this is how you can represent the Fermi sphere. So inside the Fermi sphere there are occupied energy states. Outside the Fermi sphere there are unoccupied energy states. Surface of the sphere is called as Fermi surface. The momentum space has the coordinates kx, ky and kz, where kx is a wave vector. In the quantum mechanics you have studied, kx, ky, kz are the wave vectors. So they are represented, they are related to momentum. Okay, so momentum space will represent ಮಾಡ್ತಾರೆ ಅಥವಾ wave vector space ಅಲ್ಲಿ represent ಮಾಡ್ತಾರೆ. Then what is the expression for Fermi momentum? So expression for Fermi momentum is given by EF is equal to PF square divided by 2me, where PF is the Fermi momentum, me is the mass of the electron, because we are dealing with energy of the electron, where EF is the Fermi energy. Therefore, we can get PF is equal to square root of 2me EF. So expression for momentum, Fermi momentum is given by square root of 2me into EF. Similarly, we can express this Fermi energy in the form of kinetic energy equation, that is half me Vf square, where Vf is called as Fermi velocity. Okay, ಇದಕ್ಕೆ Fermi velocity ಅಂತ ಹೇಳ್ತಾರೆ. So Fermi momentum gives the average momentum of the electrons at absolute zero. So basically Fermi momentum gives the average momentum of the electron. Fermi velocity gives the average velocity of electrons at absolute zero. You can find out the Fermi velocity if you know the Fermi energy, and also you can find out the Fermi momentum if you know the Fermi energy EF. Okay, so this is how we can represent, you can explain the Fermi sphere surface, and you can get Fermi momentum expression and Fermi velocity expression. Okay, so density of state we will consider in the next class.